The gravitational constant looks rather intimidating with its scientific notation and metric dimensions and exponents. I say that big letter G equals 6.673839, moving the decimal place to the left 11 times, and that is cubic meters per kilogram per second per second. Seems rather odd. I wonder what this means. I had started with the number 6.67384 times 10 to the minus 11. Then I found out that we don't know exactly what the value of G is. For years, we've been coming up with different numbers because it's hard to measure. This is a graph from CODATA, the Committee on Scientific Data. But one website claims to have the exact value of 6.671, while Wikipedia shows 6.674. And NASA is using 6.672. And there has been a calculated theoretical value, 6.673836, which is closer to my number of 6.673839. This number was determined by the Rydberg Constant. The Rydberg Constant seems very interesting to me. I think about the hydrogen atom and the orbit of an electron. I'm wondering about the relationship between electrons and photons. The Rydberg Constant seems to be the frequency range in which a photon can escape or fall out of orbit. This is definitely worth studying. Here is Newton's law of universal gravitation. I will just mention that the force attracting two objects together is their masses multiplied together divided by the distance multiplied by the gravitational constant. This is a drawing of Cavendish's instrument designed to measure the gravitational constant. I am only noting this for your curiosity and further study. What I am going to talk about is the formula for mass of an object being orbited. The formula says the mass equals the orbital speed squared times the distance divided by the gravitational constant. Here is a screenshot of my Android application I wrote called Orbital Speed Calculator, in which I used this formula in the program and have assigned A to the speed and B to the distance. Here is the gravitational constant without the scientific notation, and my program allows the user to input whatever value for the constant they choose. In the equation mass equals a squared times b divided by g, what does it mean to be dividing by such a tiny number? We can take the reciprocal of g, which is 14.98 billion, and multiply instead. I believe this simplifies the concept a little and allows my imagination to wander. Orbital Speed Calculator has sample orbits built in. Now I will show you where I got the numbers. The speed for a geostationary satellite is 3.0746 kilometers per second. The distance from the center of the Earth to the geostationary satellite is 42,164 kilometers. The mass of the Earth is 5.97219 kilograms, moving the decimal point to the right 24 times. I don't know where this website got this data. I don't even know how it was determined. All I know is that when 42,164 is entered as the radius and 30.74566 entered as the speed, the mass of the Earth comes out to be 5.97219. I simply adjusted the speed by 1/100th of a percent. Similarly, I could have adjusted the radius slightly, or both the speed and radius. I don't know how accurate the given speed, radius, or mass are. I am simply going with what has been given. However, if I had used NASA's gravitational constant, I get 5.973309 for the Earth mass, almost a 2/100th percent difference, Or I could have adjusted the speed to 3.07428, also a 1/100th of percent speed difference, but the speed is not what was given from Wikipedia, assuming that number is accurate to its 4th decimal place. Now, once an orbit is known as above, radius 2 can be calculated at whatever altitude you choose, in this case 6,371 kilometers, the average distance from the center of the Earth. This is where we see that 9.8196 is the acceleration at the Earth's surface. Translated into feet, this is 32 feet per second. We're taught in school, and we're told this is the acceleration near the surface of the Earth. The truth is, at the surface is a better phrase than near the surface. To be extremely accurate and joking, if an apple fell off a tree branch 8 feet high and fell into a hole 8 feet deep, it would hit Newton on the head, and that would calculate exactly into 32.2 feet per second. Here we see the metric version of 32 feet per second, 9.8196 meters per second. Here we see the math written out. The speed shown is in meters rather than kilometers. You can see a speed in the thousands multiplied by a distance in the millions multiplied by the gravitational constant in the billions equals the weight of the Earth at 5.9 septillion kilograms. The Lunar Reconnaissance Orbiter, or LRO, first orbited the Moon with a speed of 1.6 kilometers per second. From the surface of the Moon to its center is 1738 kilometers. We add 50 kilometers for the LRO's height above the Moon. We can use 1758 for our radius into the calculator. The mass of the Moon is shown here at 7.34767,309. In this case, I adjusted the speed given by 3.5% to get the value for the mass as given. I don't know how accurate the values given actually are. Perhaps all the values are off a little bit, even the gravitational constant number I'm using. Again, for the Moon, looking at the math, we have speed in the thousands, distance in the millions, multiplied by the gravitational constant in the billions equals the weight of the Moon as 73 sextillion kilograms. For the Earth around the Sun, speed is 29.78 kilometers per second. For this example, I started with the circumference to compute the radius. The circumference of our orbit is 940 million kilometers. For the radius, also referred to as altitude and in my example B, let's use 149,605,646.5. However, it's not exactly one astronomical unit as defined. Here we show the mass of the Sun is 1.98855 times 10 to the 30th power. Here we see my program calculating the mass of the Sun the same as given on Wikipedia. Here we see the calculation written out. This time the distance, or B, is in the trillions. The weight of the Sun is 1.98855 nonillion kilograms. In pounds, we have an even 4 nonillion. I want you to visually notice that when we are talking about orbits, the greater the distance, the speed is smaller, and vice versa. Orbital Speed Calculator only needs to know one orbital speed and distance pair, and it can then calculate any orbit around that body. I have wondered that since the speed is squared, and if we set the time to 1 second, then we have a distance squared, or an area. I wonder what would that area cover when multiplied by the 15 billion of the gravitational constant. To sum up, we have mass equals a squared times b times the reciprocal of the gravitational constant. So, does a speed times a distance times 15 billion equal a weight? Here are the links I used. Let's learn and wonder together. download my app, and thank you very